Hello everyone. In today's lesson we're going to be looking at Newton's second law of motion, and we're going to start out with a little scenario here. Let's say we have a box that we're trying to push across a horizontal surface. So we have our box here. Let's say that box has a mass m, and we're trying to push this box with some force F across the surface, this horizontal surface here. First of all, we should point out that just because you push on the box doesn't necessarily mean that it's going to move. You have to push with enough force to overcome the inertia of the box, which is going to be proportional to its mass. You also have to overcome the force of friction between the box and the horizontal surface. So when we push on the box, say we're pushing it to the right, we're also going to have to work against that frictional resistance, which is going to be pushing opposite the direction that we're going to try and push the box. So if we don't push with enough force to overcome inertia and friction, we're not going to be able to move the box. So this is the first thing that we have to consider when we're thinking about whether or not we're going to move the box. And if we do, what will the box's acceleration be? So when we talk about acceleration in this instance, we see that acceleration depends or is caused by net force. So again, just because you push on the box, just because you apply a force, doesn't necessarily mean that the box is going to move. There has to be a net force on the box in order for us to accelerate the box, to change the state of motion of the box. So if we have enough force to overcome that frictional resistance between the box and the surface, so if we have a smaller frictional force than our larger pushing force here, we would end up with a net force in the horizontal direction equal to our pushing force minus the frictional force. And that net force is going to accelerate the box. So this is the first point that we need to consider. The first thing that we need to consider here in our discussion today is that acceleration is caused by net force. There must be a net force acting on an object in order for that object to change its state of motion, or in other words, to accelerate. Now, we look at how acceleration depends on net force. So let's say we try increasing the force on the box. So instead of pushing with a force F, we're going to push with twice that amount of force. So now my applied force is going to be twice my original force, or 2F. If you push with a greater force, you're going to cause a greater acceleration of the box. So what we see is, with increasing force, we get increasing acceleration for the same mass. In other words, more net force. Be sure we clarify here, it has to be a net force to cause acceleration. More net force leads to greater acceleration for the same mass. And this makes sense if you think about it. If you push on something with more force, you're going to cause it to accelerate at a higher rate. It's going to increase its speed at a greater rate per unit time, right? So that's the first thing that we need to think about when we're trying to calculate acceleration, if we're trying to determine acceleration, that more force gets a higher acceleration. And if we think about this in terms of mathematical relationships, this type of relationship where one factor increases and the other factor increases by the same amount is called a direct proportionality. So we say that force and acceleration are directly proportional to each other. So if we were to graph, acceleration versus force, let's just make a real quick sketch here. So let's say we put acceleration on the y-axis and net force on the x-axis. You're going to get a linear relationship between those two variables because they are directly proportional to each other. Now, net force is not the only factor that influences acceleration. For instance, let's consider what would happen if we took another box and put it on top of our first box. So we're going to be effectively increasing the mass that we're attempting to move in this case. So let's add another box on top of our first box. So now we're going to have more mass. Maybe let's say this is 1.5 times our original mass, 1.5 times m. How is that going to influence the acceleration of the two-mass system? We're trying to move a greater amount of mass with the same amount of force. Are we going to have the same rate of acceleration? And the answer is no. We're actually going to accelerate at a lower rate if we apply the same net force to a larger mass. So this is the other factor that we have to consider when we're looking at acceleration, is mass. So to put this in a similar statement to what we had previously for net force, we would see that with more mass, we're going to get a lesser acceleration for the same net force. So, in terms of mathematical relationships, mass goes up, acceleration goes down. We call this an inverse relationship, or inversely proportional. So if we were to graph acceleration versus mass, so let's change our graph here. We had acceleration versus force before. Now we want to make this acceleration versus mass. So we're going to change our x variable to mass. We would see that acceleration is inversely proportional to mass, and we would get an inverse function, something like that, if we were to plot acceleration as a function of mass, because these two variables are inversely proportional to one another. Okay, so those are the two major factors that are going to affect acceleration in this scenario. It's the amount of net force, which is directly proportional to the acceleration, and the amount of mass, which is inversely proportional to the acceleration. So if we take these two observations and put them together, what we end up with is Newton's second law of motion. So let's write this out as an equation here, Newton's second law. Again, takes our observations of how acceleration depends on net force and how acceleration depends on mass and puts them into a single statement, a single equation, where we say A is equal to net force divided by mass, or A equals F over m. And that's Newton's second law of motion. So we can see from this equation that if we increase the net force on an object, its acceleration will also increase proportionally. But if we increase the mass on an object, it's going to see a decrease in its acceleration. Inversely proportional is acceleration with respect to mass. And that's Newton's second law of motion. Now let's talk a little bit about units of measurement here. You might remember from Chapter 2 that the unit of measurement of force in the SI system is the Newton. Mass is kilogram. Now we've seen newtons per kilogram before when we quantified gravitational field strength in Chapter 2. You might recall that a newton is actually equivalent to a kilogram times meters per second squared. And then we're dividing that by kilograms. So what ends up happening here is that the kilograms are going to cancel each other out, and we're left with units of meters per second squared, which of course is the unit of measurement that we use in the SI system for acceleration. So that's how the units are going to cancel in this equation. This is sometimes written in terms of force, so sometimes you'll see F net equals ma, or F equals ma more generally. It's the same equation, just rearranged algebraically for force. So we could, of course, also rearrange this equation for mass. If we were trying to solve for mass, we would get m is equal to F net over A. So one equation written three different ways. Doesn't necessarily matter which way you write it. It implies the same thing. Okay, so let's take a look at an example. When we do Newton's second law problems, it's a good idea to start out by drawing a free body diagram. You might recall from Chapter 2 that a free body diagram shows all the forces acting on an object as vectors, and this helps us to determine the net force on the object. Since net force is the quantity that is going to influence acceleration, that's going to need to be determined before we do a calculation with Newton's second law. So let's take a look at a similar scenario to the one we talked about previously. We've got a box on a horizontal surface. Let's say that we're going to push that box with some force F to the right, similar to what we saw in our previous example. There's going to be some frictional resistance opposing the motion of the box to the left. We also are going to have gravity, mg, or weight acting on the box. We should say the force of gravity, of course, the force from gravity acting on the box. And then a normal force, or a support force, from the surface pushing upward on the box. So a free body diagram, we consider these forces and we replace the object with just a dot. So we like to have just a dot to represent the object in our free body diagram, so it's sort of easier to visualize how the forces interact with one another. And let's make these straight lines when we draw our forces on our free body diagram. So we're going to have the normal force. Oops. I said let's make these straight lines. Fix that real quick. So we're going to have let's draw the weight first, actually makes more sense. It's going to want me to go from the object. All right, never mind. We're not going to have straight lines. Just going to draw these by hand. Okay. We're going to have the weight, mg, pointing downward, and equal opposite normal force. So we can see immediately that the net force in the vertical direction is going to be 0. The weight vector and the normal force vector are going to cancel each other out. Horizontally, we have our applied force, so we're pushing on the box to the right, and we have the frictional force opposing the motion of the box to the left. So this is our free body diagram for the box on the surface. Based off of this diagram, I can write an equation for the net force on the box. So let's give ourselves a little bit of room here. Net force, of course, we remember from previous units, is the sum of the force acting on the object. So the net force in this case, again, the normal force and the weight are going to cancel each other out. So let's make a note of that here. Net force in the y direction, vertical direction, is 0. Normal force and the weight cancel each other out. So we're only looking at the force that comes from us pushing the box to the right and the frictional force opposing the motion of the box to the left. We can just subtract the magnitudes because they're parallel vectors, or technically anti-parallel vectors. So that means they point in opposite directions, right? To the right, to the left, we can just subtract the magnitudes to get the net force. So then, using Newton's second law, the acceleration would be equal to, of course, net force divided by mass, or in terms of our free body diagram, our pushing force minus the frictional force divided by mass. So now we have an equation specific to this example that would allow us to calculate the acceleration of the object. Okay, so let's just real quick make up some numbers here. Let's say we knew the value, the magnitudes for these forces. So let's say that we push to the right, I don't know, with a force of 20 newtons, and that frictional force then back to the left, let's say it's 5 newtons. And let's say the mass of the box is, let's go 5 kilograms. Make it easy. So now I can plug my numbers into my equation. So for mass, we can plug in our 5 kilograms. And then we had 20 newtons for our pushing force. And 5 newtons for the frictional force. 20 newtons minus 5 newtons divided by 5 kilograms. So that's going to be 15 newtons divided by 5 kilograms, or 3 meters per second squared. So we're able to calculate the acceleration of the box based on the net force on the box and the box's mass.